In this video, I would like to introduce to you a new topic, which is logarithmic function. And I would like to present to you through my Microsoft PowerPoint presentation, which I make with the great care. I try to create an interesting and artistic PowerPoint presentation to attract you more interest, to be more interested in my lesson online. And I would like to share with on the audience and my students. If you register to my math courses online, you will have access to on the PowerPoint presentation as well as on the documentation about the deep knowledge of the mathematical concept. So I hope you will enjoy this video that I am about to share with you. So please bear with me 1 minute. I'm going to share the screen with you now, and I will walk you through each of the slides and explain about this content. So I'm about to share screen with you. So give me 1 minute. Okay, so this is the first slide. You see the topic is logarithmic functions. And I created on March 5th, which is yesterday. The next slide, I would like to read it and explain it to you. Logarithmic function is an inverse function of an exponential function. Therefore, if you have a function y equal b to the power x, which is the exponential function with any base here, b represents the base, and the base here could be base 3 to the power of x, or 10 to the power of x. Then its inverse is x equal log of log with the base b of y. So inverse function has the interchange coordinates. The x become a y and the y become an x. So therefore, you see this y function now interchange become an x coordinate, and equal, so equal log of the base b of the y here. So turn out the right hand side of this equation is the power on top here, if you notice it. Let's check the next slide. The next slide shows you the graphs of exponential and logarithmic functions. And the blue graph here is the exponential function f of x equal 2 to the power of x. So this is the basic function of our exponential function, which is always go through the y-intercept at 1, because x equals 0 right here at the origin. Then regardless any base, we have a function across the number 1. If you make observation for the black function here, the dark brown function here actually, and the notation for it is f with -1 on top, which is the inverse of this function. And the inverse of this function, the y function, is the inverse. It doesn't return in the log form, but in the next slide, you will see the log form. Now, just notice that the number 1 y-intercept now become number 1 x-intercept. So you can see the interchange coordinate between y and x here. So any logarithmic function, regardless any base, will go through the x-intercept at 1, just like the exponential function go to the y-intercept at 1. And the dotted ray linear line here stand for the mirror line, which is y equal x. And this mirror line reflect any point on the blue function here, reflect to the dark brown function here of logarithmic function. So the y coordinate become 1 x coordinate, and this point reflect over this point reflect over this point. Actually, the way it draw maybe because I extended so it's not accurate, but it should be reflect through this mirror line by a 90-degree angle. So any point here you reflect, pick up through the 90-degree angle with this linear mirror, then it will reflect on the logarithmic function. So let's check the next slide. What is the next slide? The next slide show you the two functions. One is the regular logarithmic function, and you notice that the x-intercept is at 1 and y is 0. Now, why they mark a coordinate here with the x-intercept as b and the y as 1? The reason is logarithmic is the inverse of exponent. So the power of the exponent is the y value of the logarithmic function. And therefore, if the y here is 1, it tells us that the y coordinate here is a 1, which is the power of the function. So if the power is 1, the base stay at the way it is. So regardless, this base here might be base 2, then this coordinate will be 2, 1. If this base here is 4, then the coordinate here will be 4, 1, because any power 1 is make the number stay the same. So that's the characteristic of it. And the same like you have another logarithmic function. And why this time it looked this way? Because this is the reflection of the logarithmic function over the x-axis. So original, it go through this one and go like bend like this. But now because it's reflection over the x-axis, so it's bent this way. And the asymptote of the logarithmic function is the y-axis. Remember, the asymptote of the exponential function is the x-axis, and the function go this way. Then the inverse of it is the y-axis is turn out to be the asymptote of the logarithmic function. And you can see that this logarithmic function approached very close to the y-axis, but never touched the y-axis. And that's why the arrow goes that way. And even though this is inverse, but you see that if the the power is 1, the base stay as the way it is. So regardless what base here, it could be base 5, then this b will represent the number 5. If this base is 6, then this b coordinate here represent is number 6 because the power is 1. So that is the logarithmic function reflection over the x-axis. And notice for the logarithmic function, the vertical asymptotes is the y-axis. For the exponential function, the horizontal asymptotes is the x-axis. So that is the two different opposite characteristic of exponential function and logarithmic function. So let's make an observation for the next graph. So again, I mark here, this is the transformation of logarithmic functions. So let's make observation one by one. So let's start with the logarithmic of base 2, which is the basic graph of the inverse of the basic graph of y equal to the power x. So we have log of base 2 here of x here, which is the red function. So this red function is opening wider compared with the x-axis, is opening wider because the base here is the basic base, the base 2. If the base is bigger than 2, which is base e, and the number of e is a natural number, is equal to 2.78, 2.78251, blah, 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 right, dotted. So this base is bigger than the base 2. And if it's bigger, it turns out remember the exponent slope is steeper when the base is big. So as well as the logarithmic function have a slope steeper and towards closer to the x-axis if the base here is getting bigger. So the ring function here have a big base, have the base bigger than the red function. And the blue function here have a base even bigger, which is base 10. So from base 2 to base 10, you see the slope of the base 10 is steepness and very close to the x-axis. So the function bend this way for any function, it goes to the x-axis at 1, x-intercept, and it bend towards, it keep going, but if the base is big, the function get closer to the x-axis. If the base here is small, the logarithmic function get further apart from the x-axis. So that's the observation we make through these three functions. So let's take a look at the next slide. Again, the next slide shows you another transformation of the logarithmic function. And you can see that in this transformation, the vertical asymptote instead of the y-axis now move to the right by 2 units. So the vertical asymptote now will change at as the x equal 2 is the equation of this asymptote. And therefore, instead of the x-axis, instead of at 1, move 2 units. So therefore now the function cut the x across the x-axis at number 3 and y is 0. So that shows a horizontal shift or translate to the right by 2 units. So let's take a look at the domain of the logarithmic function here. The domain of it, you can see the function only exists after the number 2. After the number 2, we have the existence of the function. But on the left side of this asymptote, there's no function. There's no existence of this function. And therefore, the domain of this function equals start from the number 2, and it's not a square bracket, but it's the round bracket show that it excluded the value 2. Because at the value 2, the function doesn't cross it. So the x start from excluded from the number 2 towards on the way to the positive infinity, this way, to the right. So it start from the asymptote here, but excluded this value, not include, but excluded. And then x will belong to any number after the number 2 on the way to positive infinity. So that is the domain of this logarithmic function. What about the range? The range is the set of value of y of this function. And the set of value of y of this function is on real number from the negative infinity to positive infinity, because this function keep going up here and keep going down here. So that is another transformation. Let's take a look at another transformation of logarithmic function. Again, this show a straight line linear the mirror line. Why do we have a mirror line? Let's take a look at the logarithmic function of the red one here. The red logarithmic function here stands for the inverse function of the exponential function here. So if the exponential function is a blue function, and this is the decay function, right? It's not the row function, but it's a decay function because the base here is less than 1, bigger than 0 and less than 1. So the base here is a fraction, tiny fraction, and any tiny fraction have the shape of the decay exponential function. So this blue function has its inverse at the red function here through this mirror line, and the red function denoted as the f to minus 1 on top, which is the inverse, and it equivalent to the return of log of the base 1/2 of x. Next, we will talk about the pH power of hydrogen scale. So for example, this is the application of both exponential and logarithmic. So x have a pH value of 8, 3.16 times more alkaline than the blood. So the blood have a 7.5 pH value, and the X have a 8 pH value, and it 3.16 times level of alkaline than our blood. In coffee, the coffee have a acidic level of 5.1 pH value, which is calculated using the logarithmic function. You can calculate it, become 31.6 times more acidic in coffee than in milk, because milk have a smaller pH value, 6.6. So this is the application of logarithmic functions, so that you can see how useful it is. Next slide, we talk about exponential and logarithmic functions can be used to calculate population growth, chemical dissolved in a solution, half-life of radioactive substances, money invested, alcohol, caffeine level remains in the body, or carbon dioxide levels in the atmosphere, or radioactive decay, and many others useful in the real life problem. So that is about the application of these two functions. So let's check the next slide. The next slide, I talk about measurement on the Richter scale. For example, a mosquito buzzing 20 decibel in loudness is about 100 times louder than the threshold of hearing, which is measured at 0 decibel level. Let's say a whisper of somebody, whisper to someone, have a 30 decibel measurement. It's calculate, if you use logarithmic function, you can calculate, convert it into 0.001 times as loud as the conversation of 60 decibel. So this is the useful of the application of logarithmic. Will allow you to calculate how many times the loudness of the intensity of the loudness of anything. Okay, so let's check the next slide. So the next slide, I introduce to you about the laws of logs. We have a lot of things to remember for the laws of the logs, which is the rules how you calculate the logarithmic function. The exponential function is b to the y equal x. If you convert this function to the inverse, you will write, and the way you write, you will say, I am going to take log base b of x, and log base b of x evaluate equal y power. So see, this is exponential function with the power of y. So the way you write in log, you will write log, and below level a little bit with the base b, which is the same base of exponential here, exponents here, the base b. To take the log of base b of the x function will result into the y power of the exponent here. And that's the way you can write in form the exponent form to the logarithmic form. So therefore the arrow go both way, I show here. So this is the way you write in log, and this is the way you write in exponent. Now, the law of log says that if you take the log of any base of the number 1, then the answer equals 0. Because if the base is 3 to power 0, then it equals 1. Let's say the base b here is 10. 10 to the power 0 also equals 1. Or 100 to the power 0 also equals 1. So that's how you interpret the evaluation here. So the next law says that if you have a log of two numbers multiplied together, the log of a multiplied with the log of the two numbers a times b, it's the same as you separate them and you add them. So addition become multiply. Log a add log b, you can join them in one log and join the a multiply with b. Now, when it's written in log without the base, it represents base 10. But for the particular number, they don't want to write base 10. And if you write base 10, it doesn't change anything. It's okay. But should people have a convenient habit that we don't write the base 10? It's like a square root 2. We don't write the number 2. For the root 2, we just put square root without any number. But for the root 3, we have to put root 5. We have to put the same like log here. If base 10, they don't write it, but that it means base 10. So the addition of two separate log A adding with log B will be equal log A times B. Similarly, the division of log A divided by B will be equal log A minus log B. Now, this is just the introduction slide for you to get some idea. As we get going and we actually put in the number, you will understand this law better. But I want you to take a look at it because it's extremely important if you can remember this law to perform the logarithmic calculation computation. If you keep in your mind all of this law, it won't make you easily make a mistake because you know on the laws of logarithmic function. To be honest, at the high school level, we require you to remember this law of logs. Unless when you go to university, there's so many formula and they allow you to use a cheat sheet. But for this law, log's law of exponent and the rules for adding, calculating exponent, as well as the rules for computation of the logarithmic, students should remember. It makes easier when you calculate, compute. Okay, so let's take a look at the next slide. The next slide have shown you the other law. So let's say if you have a log of a to power n, then you can bring the n in front of the log and write like this. So this written form the same as this written form. It is equivalent and therefore there's a balance sign here. Whether you write like log a to power n or you can bring the power n and put in front the log, that's acceptable. The next law is say if you have a log base b of a, it will be equal to separate log and you can change the base b become the base x. So this we call a base change formula. For the base change formula, you can rewrite this log with the different base. So instead of base b, you can write base x. But when you do that, you make sure you separate these two logs and you write them separately, like log base x of a divided by log base x of b. So in order to use the base change formula, you have to separate them like this. So just treat the log of another base for this a divided by the log of another base x here for this b number. And that's how you divide them. You write, whether you write like this or you can write like that. The arrow here should be go both ways. Again, another law is, let's say you have a log of base b of a, logs with the base b's of a, you can change the positive log become a negative log if you twist this base with the inverse fraction. So instead of b, it will be 1 over b of a. And make sure you put a negative in front when you twist the base inverse like that, you have to have a negative sign here. So that's another the laws of log. And there's many laws. You can see that if you have a log of base A of the same number, then the evaluation of it is always equal 1. So if you see these two numbers are the same, your answer will be the evaluation of this log will be equal 1. And similar, if you have the base B here and to the power of log of B to the A, then you know the answer is just A. At this time, I just want to introduce you on of these law of logs and go through with you quickly. But when I show you the operation, the calculation, the computation on the board, you will know, you will understand how we apply this law into our computation. So let's say if you have a ln. Now, what's ln mean? Ln is similar like log. However, the base of log is base 10, but the base of ln is base E, which is 2.78, like the number, the natural number. So ln of AB, the same, like you separate them, you write ln A plus ln B equal ln A times B. So, oh, this is my mistake here. It should be ln A divided by ln B. Ln A divided by B equal ln A minus ln B. I will change this for you. I will fix this mistake here. Now, log B of A will be 1 over log base A of B. So you can reverse the base here, these two numbers here. The base here is B of A will be equal the inverse, the fraction of 1 over the log A of B here. So you see this base here is B. For the base here, it turn out A instead of B. So you can reverse like that. If you can twist the fraction inverse, you can rewrite like this. So when you learn on the boring math here, you look at the beautiful natural view here. I incorporate in this slide. And I don't know about you, but I like it very much. So next slide, there is another beautiful scenery here. And on the left is on the log written in the big capital in bolded letter. So it looks obvious to you. So if we have log A of A is equal 1, B of log B of A equal A. If you write log A of X divided by log A of Y, you can use the base change formula. So this base A, you can change into base B of X divided by log base B of Y. So I like this beautiful waterfall here. So the last slide here, I give you another natural, beautiful view for you to refresh your mind. When you look at this natural view, you refresh your mind. So your mind gets less tired and you can relax and read my notes here. I hope you enjoy learning this Microsoft PowerPoint presentation about logarithmic functions with fantastic natural views. Mathematics present in arts, science, reflection in all aspects of our life. So this is the end of my PowerPoint presentation about the logarithmic function. And I hope you enjoy looking the fantastic natural view and try to understand about the mathematical concepts. Thank you for watching, my audience. I'm looking forward to see you in the next video. I will show you on computation of logarithmic functions. So thank you for watching. And let me get back to you in a minute before I say goodbye to you. So this is the end of our presentation, and I hope that at least this Microsoft PowerPoint presentation I make, it looks attractive and to serve you with the purpose to serve on my student in the course of Math 12 with calculus. And I hope that like this will make you feel interesting about math, and you will sign up to my online math courses. And if you have a chance, just visit my mathteaching.ca and stay tuned for our next video about the computation of logarithmic function. Thank you for watching, and bye for now. Oh, sorry.